Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Doppler Jr., your math tutor, and I am an instructor of mathematics at the University of Liberia. In today's lesson, I want to look at the proof of the derivative of the natural exponential function e raised to the power x. So we say if a function is y equal e raised to the power x, which of course this function now is a natural exponential function, we can find its derivative by using the first principle of derivative. So we know that the first principle of derivative is f prime of x is equals to the limit of f of x plus h minus f of x divided by h as h is approaching 0. So now we have the function f of x. Now, when a function y equals to e raised to the power x, this y can be replaced with f of x. So this is the same as f of x. So now we know f of x is equal to e raised to the power x, but we don't know f of x plus h. So we can just replace this x with x plus h. So we'll replace this now with x plus h. So wherever we see x as well, on the right hand side, we must replace it with x plus h. So we now put it in the expression f prime of x equals to the limit of, this is e raised to the power x plus h minus e raised to the power x all over h as h is approaching 0. Now at this point, we remember that when we were doing limits, we proved one of the standard limits, and we had it to be the limit of e raised to the power h minus 1 all over h as h is approaching 0. We prove that this is equal to 1. So if you have some doubts on the limits, you can check our previous lessons. So based upon this particular standard limit, we want to rewrite this particular limit such that we can bring in this standard limit. So we have f prime of x is equals the limit. Now e raised to the power x plus h can be rewritten as e raised to the power x times e raised to the power h, because when the bases are the same, we can just take one of the bases and add their exponents. So this can be rewritten as this minus e raised to the power x all over h as h is approaching 0. So f prime of x now becomes the limit. So we can factor out e raised to the power x, e raised to the power x. And then what will be left here is e raised to the power h minus 1 all over h as h is approaching 0. Now what do we have? This e raised to the power x can come behind this limit. It will be e raised to the power x, the limit of e raised to the power h minus 1 all over h as h is approaching 0. So we know that this entire expression is just equals to 1. So it's like e raised to the power x times 1, which is just equal to e raised to the power x. So therefore, we can conclude that if y is equal to e raised to the power x, then y prime, which is its derivative, is equal to e raised to the power x. So this works for the cases that this coefficient of x is 1. The coefficient of this x is 1. What if the coefficient of this x is not 1? For instance, you have e raised to the power some ax. What if you have a2 represents real numbers? So if a is representing real numbers, wherein a is not equal to 0, and a is also not positive 1, because when a is positive 1, is just equal to e raised to the power x. So we can rewrite this thing again, e raised to the power ax, the same way, and then we differentiate the exponent e raised to ax such that y prime would just be a e raised to the power ax. But what if this a this ax was not just a real number? What if it was a function? Assuming you have y equals to e raised to the power u, assuming u is a function. Example, you have x plus 1, you can be x plus 1, you can be x squared minus 1, you can be sine of x, you can even be e raised to the power x, and so forth. Assuming that u was a function, then we can say in general that y prime is equal to e raised to the power u times the derivative of u. So when you rewrite e raised to the power u, then you differentiate this u. So this is a general form for finding the derivative of a natural exponential function. So in next video, we will be able to solve more problems involving finding the derivative of a natural exponential function. Thank you very much. See you in our next lecture.